will indeed, yeah, got it. I will indeed talk about two different techniques today: species sensitivity distribution concept and the principal response curves technique. And yeah, they both have the same aim. They both want to describe the effects of chemicals at the community level. The species sensitivity distribution concept does that using lower tier data, so toxicity data, either acute or chronic. And the principal response curves is more a statistical technique to analyze the data you gathered in a mesocosm experiment or microcosm experiment. And that is, of course, higher tier data. To start with the species sensitivity distribution concept, if for a chemical X, we have this availability of toxicity data. Typically for a fish, you have two data points, for invertebrates a few, and for algae a few. And if you want to do a risk assessment for this chemical, what is the safe concentration of this chemical for aquatic ecosystem? And so is it 12 or is it 12 divided by 10? That is, of course, done in the first tier, using the lowest value for standard test species and then use safety factors or assessment factors. But the disadvantage of that method is that you don't use all the other data. And we know much more. We know more than that the fish species is the most sensitive organism, because we also have data for invertebrates and other fish species, algae. So how can you do a second tier risk assessment, as we call it, using all the data? And that is, first, this is the distribution of the available toxicity data. So you see on the x-axis the log toxicity data, on the y-axis the relative frequency, and you see that all around the average, it's more or less log normally distributed. So you can draw a log normal distribution through the data. And that is the same data as shown over here, of course. Yeah? So you see 12, 25, and 55. And that are, I'm not sure whether you see my pointer. Yeah, this is the 12, 25, and the 55, of course. And then we have two very close to each other, and that's these two, 219 and 268. So we can draw a log normal distribution through those data, and we can also plot it cumulatively. So these are the same data as I showed in the table, had the 12, the, what was it, 25 or so, 55. And so these, every point is an EC50 value. And this is the least sensitive organism, and this is the most sensitive organism, the fish. And you see that the cumulative distribution fit is quite nicely through all the data. And this is what we call the species sensitivity distribution. But in statistical terms, it's a cumulative distribution function. It always ends up to 1, of course. And the advantage of this is that you can interpolate between the values of the toxicity data. So you can not only say, okay, this fish has a sensitivity of, what was it, 12 microgram per liter, but you can also say, if you take this one, if we want to protect 95% of all species, then that corresponds to this concentration. And you can also say, okay, the average species has a sensitivity of this. Also, the other way around, if you have measured the concentration in the environment, you can say, okay, if I measure 1 microgram per liter, which is a log of 0, then the potentially affected fraction is 30%. So you can use it both ways. And you can say, okay, I want to set a protective value of 95%. Then you can calculate the HC5, as we call it, the hazardous concentration, 5%. And you can say, okay, that's my standard. If you say, okay, These are based on EC50s, so I don't want 5% of the organisms to be exposed at their EC50 or higher. I want to take the HC1. That's also fine, of course. You can also take the uncertainty into account because the SSD also has an uncertainty. This is different data, of course, but if you calculate the HC5, the average one is over here. But if you want to be very sure, at 95% sure, then your standard could also be taken over here at the lower end of the distribution. So it's really important to note that you can use SSDs in two ways. Standard setting, just make your protection goal and calculate the value that belongs to that. Or when you have measured concentration in the field, you can calculate the potentially affected fraction. And in this case, if you have measured this concentration, that corresponds to 30%. You also see that in the past, different distribution functions have been used: logistic, normal, triangular, and many more. And nowadays, normally people will use log normal distributions as they are the most robust ones. You see also in this case, it doesn't matter that much. Okay, so here we have the same SSD, well, different SSD, but also with a confidence interval, which is quite large here because you see a clear misfit. And then you can also calculate the confidence interval of the HC5, and you can take the lower limit if you want to be really protective. The advantage of SSD is that it makes better use of the available data because it doesn't use just the lowest data point and use an assessment factor, but it uses all data points. So if your lowest data point is an outlier because of an experiment that is based on nominal concentrations, while the measured concentration would have been much lower, for instance, or higher, then at least if you have to use the distribution, you also use the data of the other experiments to come to your safe concentration. The second advantage is that the generation of additional data is encouraged because your HE5 becomes more precise when you gather more data. So even if you already have your SSD and the uncertainty is very high, then it makes sense for instance, industry to test more species. So the confidence interval becomes smaller and the uncertainty is lower. While if you have a most sensitive species and you just divide it by an assessment factor, there's no incentive to gather more data because it can only be lower than the most sensitive species already. So you can extrapolate effects to untested species, but be aware that it is a statistical approach. And the community is represented as a bag of species. As an ecologist, it's a completely useless approach, of course. But as a risk assessment, it's a very useful approach. So there's no ecology in this. And it's all based on single species test, and the same disadvantages that adhere to a single species test also comes with this species sensitivity distribution approach. So it lacks ecology, no indirect effects, etc. What is really important is the selection of species. This is an insecticide, and if I take just all the data from the ecotox database of the US EPA, I get this SSD, and we see clear misfits. And you see that it's a binomial curve and not a normal distribution, a log normal distribution. It's two distributions in one. And I would even say, if you look at this, then you see that, not surprisingly, for insecticides, the arthropods are much more sensitive than all the other organisms, even including fish. Some of the fish, as you see over here, are quite sensitive. others are not so sensitive. But you see, oh no, these are the vertebrates. Some of the vertebrates are very sensitive and others are not. The same for the non-arthropods invertebrates like snails, etc. And the algae, not surprisingly, are also not so sensitive to the insecticide. But arthropods, the insects and the crustaceans, are extremely sensitive to venitrotion. And if you want to use this for risk assessment, then of course you should only include the arthropods. Otherwise, you're fooling yourself. If you present an SSD like this, then every expert will see this is a clear misfit. So here protecting 5% of all the species is also a bit silly because you have to focus on the most sensitive group as shown over here. So for risk assessment of insecticides, we only include arthropods. For herbicides, not surprisingly, only include primary producers. And for fungicides, that's a case-by-case decision because fungicides are really a strange group. We also applied a species sensitivity distribution concept to predict antibiotic resistance. A former PhD student of mine, Andrea Rico, did that. And we did that to predict the occurrence of antibiotic resistance in aquaculture production. And this is the distribution of the environmental concentration, and we predicted that by an exposure model. This is the SSD, this is the distribution, and this is the species sensitivity distribution based on minimum inhibitory concentration for different genera. And personally, I don't work every day with the minimum inhibitory concentrations, but the MIC values are the lowest antibiotic exposure concentration that prevents the visible growth of a bacterium during the incubation period. So it's a bit of a LOAC in risk assessment terms, I would say. So it's interesting, of course, to confront the distribution of the exposure concentrations with the SSD based on the MIC values, and that is the risk of developing resistance. That's the overlap, this part, the black part. So these are the SSDs based on MIC values. We did that at a general level. We thought that was the most appropriate one for different chemicals used in aquaculture in Asia. This is all about Asia. And these are the risks that were associated with these SSDs based on the predicted pond water concentrations and the environmental water concentration. So the pond water concentration is the concentration of the chemical inside of the aquaculture pond. And the environmental water concentration is the concentration that is expected to an adjacent water body when the water is pumped out of that pond. And of course, the risk for the environmental water concentration should always be lower than the risk inside of the pond. And you see that in Asia, by normal use of these chemicals, you see that the risk of resistance development is very high. And even in the environmental water concentration, so the water bodies adjacent to the aquaculture ponds, this risk for some chemicals is quite high. For other chemicals, it's almost zero. But for some chemicals, like this one, these two especially, it is quite high. So that's how we applied the species sensitivity distribution on microbial data. Do we take questions at the end, or shall we deal with questions on the species sensitivity distributions now?
I think we can take questions at the end.
Okay. So now we predicted the risks of chemicals, whether it's death or antimicrobial resistance, at the community level using these lower tier data. And these were all data based on single species tests, whether it was based on antimicrobial resistance or mortality. Now, I will focus on the use of the principal response curves technique, which is a completely different technique because it focuses on the analysis of the time-dependent multivariate response of a biological community to stress. And I know that it's a mouthful, but I will try to explain to you. If we do an ecological risk assessment of chemicals, we want to estimate the effects on the presence of species. Do species die? Their abundance, do they partly, the population, does it partly die or completely? And their role within the ecosystem. That is also very important. And for that, at least within my group, we use semi-field experiments. So for us in the past, the experiments that we did with pesticides, this was the scenario more or less. The pesticide is sprayed, and through spray drift or runoff, part of it comes into the aquatic ecosystem, and we wanted to do a risk assessment for the aquatic ecosystem. There's many types of semi-field experiments. These are the experimental ditches in Wageningen, which are quite large. These are soil systems. These are plots, terrestrial plots, and these are very small microcosm planktonic systems, only of 8 liters. So this one is 8 liters, and this one is 60,000 liters. So they can vary in size considerably. The typical thing, if you do an experiment with mesocosms, you get big data sets. And this is the macroinvertebrate data set from an experiment we did a while ago with chlorpyrifos, of which I will show you the results later. And typically you sample on a day a few units, in this case 12 mesocosms, and they all belong to a treatment, with one being the control, lowest concentration, medium concentration, medium high concentration, and a high concentration. So the replication was quite limited during this study. So 12 systems, and we sampled them, I think 12 or 13 times. So that results in 140 samples or so. And we found in these samples almost 200 different invertebrate species. And these are mayflies, midges, etc. So there's 200 of these species. So this is almost 1% of the total data set. So you end up with a huge data set. And what can you do with it? You can make the graphs of 200 species, but that's not really helpful because then you're also drowned into the details, because you want to extract a response from that data set. And this is the experiment, which I already introduced briefly using the experimental ditches. This is me as an MSc student, so it's a while ago that we performed this experiment. It was a single application of the insecticide chlorpyrifos, 4 ditches control, 2 ditches 0.1, 0.96, and 44 microgram per liter. We were expecting effects, especially at the 2 highest treatment, because the LC50 of the water flea was 1 microgram per liter, so this was much higher. And we sampled the invertebrates 1 month before the application until 6 months after that. And we log transformed the abundance data, not surprisingly. These were the effects on a number of species. So what we saw is on average between 30 and 40 species in the mesocosms, a bit going up in during the experiment, and also going down during the end, but that's because of autumn. This is the summer, so it's not surprising that it went up, at least in the control. And you see clearly effects on in the 2 highest treatment levels, the 6 and the 44 microgram per liter, on the number of species. So a very crude endpoint, just the number of species that we found in the samples, the number of invertebrate species. We also looked at the Bray-Curtis index, and also for the same, also for the two highest treatment levels, we clearly found effects at for the Bray-Curtis index. Maybe recovery towards the end, but this can also be the effect of autumn, to be honest, because at autumn everything goes down, so then often the control also goes towards the treatment. Then, because you know that insecticides are only toxic to arthropods and not so much to non-arthropods invertebrates, we also did an analysis only using the arthropod data, and then you see the effects are much larger. So then you can also focus just on the most sensitive group of species, which makes sense, I think, to do. But still, no effect of the 0.9 microgram per liter, and also not of the 0.1 microgram per liter. This is the old way of analyzing this data, just using diversity indices, number of species, number of just abundance values, total abundance, that kind of stuff. So that we found that generally the NOAC were 0.9 microgram per liter, no effects at the two lowest concentrations, and the effects for all invertebrates were smaller than for the sensitive arthropod taxa only, not surprisingly. The problem with these endpoints is that if you have indirect effects, some species go down, other species go up, they mask, the species that go up mask the effect of the species that go down. They compensate for that. For instance, in our experiment, we had a decline of the shrimp and the mayfly, and we had an increase of flatworms and of snails. And then the increase of these two, they mask the effects of the species that go down. For instance, if you take the total number of species, then the one will mask the other, of course. So the information at the species level is also lost. If you look at the Bray-Curtis index, you don't know which species is making the difference between the different treatments. So we felt that there was a need for a method that focuses on responding species without assigning them a priori, of course, and still showing the information at the species level. And ordination can do that. Ordination is a method that is already present for a long time, maybe 100 years ago. PCA was principal component analysis was developed, so it's not a new technique. Some of the techniques that we use are new, but the redundancy analysis, for instance, is developed in the 80s, I think, or so. But so we first applied a relatively standard method, redundancy analysis, which is based on principal component analysis, but as we call it, it's supervised. And supervised means that it focuses only on that part of the variance that we're interested in. If you look at this diagram, this is a very difficult diagram. I understand that, but without going into details of the whole ordination, what ordination tries is to extract gradients out of the data set that maximizes the differences between samples. So the first axis is extracted, and you see this is the control going from spring to autumn. So the first axis is merely the time, just season, going from spring to autumn. Then the first axis, for instance, explains 20% of the total variance, and from that remaining 80%, you can still extract a second axis. That is done over here, and then you see clearly the effect of chlorpyrifos, because this is the control, this is the 0.1 microgram per liter, this is the 0.9 microgram per liter, 6, and a 44. And the further away the samples are projected from each other, the more different their species composition is. So this sample and this sample have almost an identical species composition, but this sample and this sample have a very different species composition. So you see clearly that there is a nice gradient of an effect from 0.1 being a bit below the control, then 0.9 being even further away, 0.6 being more further away, and 44 microgram per liter being really far away. So you see clearly the effect of chlorpyrifos, but you see also at least a start of recovery, because you also see in the one but highest treatment level and in the highest treatment level, they go back to the controls again. So we see a dramatic effect, but also a bit of recovery. Maybe not complete at the end of the experimental period, but at least partially. Whether that is real recovery or just because autumn hits in, that's a second question, of course. What you further see is also some species names here and there. And if a species name is projected here, it's very abundant in these samples and not so abundant in these samples. So these are the species that responded to chlorpyrifos the most. And these are Ephemeroptera, some midges, some water fleas, etc. So these species really suffered from the chlorpyrifos addition. These species increased in abundance because of the application of chlorpyrifos, and that's not many of them. There's only 2 snail species who did that. The species projected over here were mostly present in spring, and these species were mostly present in, I would say, summer and autumn. So that's how you can interpret this diagram. I hope that's a bit clear. So that was a really nice result. We published this in a paper in Environmental Toxicology and Chemistry, and being really happy, we applied an existing statistical method for this data set. You can also do Monte Carlo permutation testing and other types of testing, and then you clearly see an effect of chlorpyrifos with indication of recovery at the end. And you can even calculate NOAA community values. And you clearly see now that the NOAA community value is 0.1 microgram per liter. So based on these overall endpoints like number of species, Bay-Curtis index, etc., it was 0.9 microgram per liter. And you see that this method is more sensitive because it also showed the effects of the 0.9 microgram per liter treatment. So this one. And the other techniques failed to do that. So that's all nice. But then we did an experiment a bit later. And this was the result. And well, you can look at this for 5 minutes, for 2 hours, but it's really difficult to see the effects of the chemical in this plot. And that is because time, in this plot, time is nicely going roughly from here to there. And that's really nice because then you have time and treatment separated from each other. And that is quite nice for the interpretation. Over here, time is, this is the, if you look at the control, it's this one, it goes from here, 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 back, and then here. And so it's not so straight in the diagram, and then it's really difficult to interpret it. So me and Kayo de Braak, who is a specialist in ordination, were searching for a method that time was a single direction in the diagram. And that is the principal response curve. And that is based on redundancy analysis, but doing it a little bit different from the method that I just showed. So we focused with the method, the principal response curves, only on the deviations of the treatment from the control in time. If you are a statistician, then now you can, if you're not, then still, it's not so difficult as it looks. This is the whole matrix. So we have a count of a species, K, at a time D in a treatment D and a replicate G. So that's the whole matrix. I showed 1% of that in the beginning. That is modeled as a control. So the count of species K at time point T in the control and a deviation. So this is the part we're interested in. And the deviation falls apart for a deviation for every treatment and every time point, and the weight of each species with that. K is the species, and of course an error term. And if you display that in a diagram, you get this. This is the CDT value, so this part. So you see that by definition, the control is 0, because we only model deviations from the control. And every treatment has a CDT value for every time point. And so this is week -4 until week 24. So you see every treatment deviates a bit from the control. And you can also assess the significance. And you see nicely for the 0.9, it's significant for period of time with recovery, the 6 as well with recovery, and the 44 microgram per liter with partial recovery, maybe towards the end. At least it's not statistically significant anymore. But also keep in mind that it was a low replicated study, only 2 replicates per treatments. The control was replicated 4 times. This diagram resembles the original diagram quite a lot, of course. If you just change this diagram a bit to the right, turn it a bit to the right, then it much resembles this one, of course. But now at least the control is exactly a straight line from left to right with time. And then we have, of course, also the BK values. These are the species weights with the principal response curve, and we can show them on the right. Canis horaria, Cleondipterum, and Nauplius have a high weight with this diagram, so they are indicated to have been negatively affected by chlorpyrifos. We saw that one species, Bithynia, had a negative rate, and so it increases in abundance in the higher treatment levels. And if you keep in mind Canis horaria, Nauplius, and Cleondipterum, in the original diagram, they were, of course, also over here. And these species also showed a negative effect of chlorpyrifos, but not as strong as these ones. And these show also a positive effect, but not as strong as this one. So now the NOAC community is 0.1 microgram per liter. So PRC is more sensitive compared to the number of species, these overall indices. The method, to explain the method is maybe quite complex, but to interpret this is quite easy. Especially if you leave the species out, it's really easy to communicate this with non-experts. If you leave out all the details, and even with the species diagram to the right, if you do a bit of explanation without knowing the details, you can quite easily explain how the people should interpret this. That's really an advantage. Well, if you show this to someone, a risk assessor or so, then they get lost, of course. The information at the species level is still shown. That is also because we know that 0.9, 6, and 44 microgram per liter are different from the controls during the summer, but we also know which species are causing this difference. And that is really an advantage over using, for instance, non-metrical, multidimensional scaling. And species, if you want, species can also be weighted differently to express the importance for ecosystems. So you can weigh some species with a higher weight, some species with a lower weight. You can also focus on a certain part of the species. This is a PRC we did for all species. We also did a PRC only on the arthropods, of course, and only on the non-arthropods. And then you see nicely that the arthropods, all of them, are negatively affected. And with the non-arthropods, some of them are positively affected because of indirect effects. And because the snails, of course, can profit from all the arthropods going down because of the releasing grazing pressure. We also did do that nowadays. We use this technique for analyzing bacterial data, for instance. Here we did an experiment with fluoxetine, which is a psychopharmaca. And this is the PRC on the bacterial data, and you see clearly an effect of the highest treatment on the bacterial data. I added this because you can also interpret PRC more in quantitative terms. This is a principal response curve showing the effects of fluoxetine on bacterial communities in sediment samples. Of all variants, 36% could be attributed to sampling date. So that's shown on the x-axis. 20% of the variation could be attributed to treatment. So that means that treatment and time together explains 56% of the total variance. So 44% of the total variance could be explained by differences between replicates. So you can really partition your variance. But we are interested in this 20%. Of this 20%, 1/3 or a bit more is displayed on the vertical axis. So that's displayed. So a bit more than 1/3 of the treatment variance is displayed on this vertical axis. That leaves us, of course, with 63%. And that is this error term. And of course, you can extract a second PRC from this, but I won't go into that now because that complicates things even further, but that makes the method also complex again to interpret. But be aware that you can extract more than one PRC if you want. So you know exactly the amount of variance that is displayed on this vertical axis. And then you can also add Monte Carlo permutation tests or other types of multivariate tests if you want, that also indicated that a significant amount of the treatment variance was displayed on this y-axis. And you can also do individual permutation tests, and then you see that these 2 points are significantly different from the control. And that's what I had prepared. Are there any questions?